Merci d'être là. Je vois que j'ai que des amis dans cette salle, ça fait vraiment plaisir. En face de moi, il n'y a que des gens experts de domaine, des physiciens, des mathématiciens, des biologistes, des financiers, hommes, femmes d'affaires, politiques, chacun suivant son expertise. ENESIA, c'est une école d'intelligence artificielle qui a pour but, au départ, de faire de l'IA sur la comptabilité. Mais nous voulons faire de l'intelligence artificielle également appliquée à de la médecine, appliquée à de la biologie, appliquée à de l'histoire. J'ai l'honneur d'avoir Franck Ferrand d'ailleurs dans cette assemblée et avec qui sûrement on va travailler autour de l'intelligence artificielle, la réalité augmentée à l'histoire et dans les archives. Donc on veut vraiment faire de l'intelligence artificielle un petit peu appliquée à tous les domaines. Donc ENESIA a pour objectif également de réunir des scientifiques de premier plan. Nous en avons ici, parmi les meilleurs du coup, des experts en IA et une grosse ouverture vers la recherche et l'application de cette recherche au monde de l'industrie, de la finance. L'idée, c'est certes de faire de l'intelligence artificielle, mais de voir également comment la science fondamentale, les différentes disciplines, les mathématiques, la physique, peuvent nous aider à faire des intelligences artificielles extrêmement perfectionnées et applicables directement à des secteurs comme la biologie, la finance ou la comptabilité. He's one of the best physicists in the world. So he's a string theorist, specialist of theory, which is in fact a kind of unification between quantum mechanics and general relativity, the laws of the universe from the atoms to the galaxies. And he developed several theories, especially with in the field of black holes, in the field of Navier-Stokes equations applied to general relativity. He works at Harvard University. I will leave you, Professor, presenting your conference about black holes. Thank you very much.
The floor is yours.
I just want to say it's a pleasure to be here talking to you all tonight. And I want to thank Nico and Catherine for their hospitality, and I had a wonderful visit to the ENESIA school today, and it's exciting to see what is being done here. So I'm going to talk today about work on black holes, which I would argue are the strangest objects in the universe. So now, interestingly, black holes have moved to the forefront in many areas of modern science. They're interesting to philosophers. They're interesting to people who are trying to understand information theory, quantum information theory, to computer science, to string theorists, mathematicians, historians, philosophers, and especially in the last few years to observational astronomy. So not long ago, we didn't see many black holes at all. Is that aimed right? Yeah, there we go. Okay. So let me start with what is a black hole. So on the moon, or let's start on the Earth. On the Earth, if you can jump upwards and get going at 11 kilometers per second, and there was no friction from the atmosphere, you could keep on going forever and fully escape the gravitational field of the Earth and continue indefinitely through outer space. Now on the moon, there's less mass, and the force of gravity is weaker, and you wouldn't have to jump so hard, so fast. And you would only have to go at 2 kilometers per second. And it was realized actually by Michel, a French person, I believe, that in fact, they already knew long before Einstein, they already knew that what the speed of light was. And they said if you had a massive enough object, nothing could get out of it. And therefore it would just appear like a black object. No light could escape if it were sufficiently massive. Now, then things became much more interesting 100 years ago when Einstein wrote down his field equations, and he wrote them down in 1950. He said nobody would ever, they were too complicated, though elegant and beautiful, extremely complex. He thought nobody would ever find an exact solution, but Schwarzschild proved him wrong just a few months later. And he found the black hole solution. Now, usually in physics, when you get to that stage, when you write down an equation and you solve it, the hard part is over. Then you've got the solution, you just look at it, you look at its properties, and you're more or less done. Not so with black holes. People argued about them, whether they existed, what they meant, what this weird solution meant. They argued about the classical theory of black holes for 50 years before they understood what they were. Then Stephen Hawking came in with the quantum black holes, and now we're still arguing about that 50 years later. And I just want to say that to give you a sense of what a long scientific project this is. We're not at the end of it. We've been learning things so fast, even people in the field are hard to absorb it, have trouble absorbing all of it, but it's been going on for 100 years, and maybe in another 100 years, we'll completely understand black holes and we'll move on to something else. But that is not yet in sight. There's still many things that we don't understand about black holes. And also, people didn't, Einstein himself, in a paper that I would have flunked him for in my general relativity course, said that black holes can't exist. Not that Einstein wasn't a very smart fellow, it's just that they didn't understand black holes then. It was not really until Penrose, Wheeler, Hawking, so on that people understood what they really were. And people didn't believe that they, even if they existed on paper, that they existed in the sky. Now we know at this very moment, we're all orbiting around a giant black hole in the center of our galaxy. We see them, there are thousands or millions, we don't know how many, up there in the sky, and we're starting to really zero in and measure their properties. Now, in the quest to understand black holes classically, that kind of came to an end in the 60s and 70s, and the conclusion was that a black hole is nothing. Now, I don't mean like the nothing here, there's air in the room. I don't mean nothing out in outer space, there's a vacuum. Literally, space comes to an end, space and time come to an end at the edge of a black hole, and there's nothing inside. And for that reason, black holes are completely different than any other object in the universe. A star, for example, every star, there are many stars up there that are the same size as the sun in the middle of our solar system, but they are all different in innumerable ways. They have different numbers of carbon atoms and they're moving in different directions, different magnetic fields, they're spinning around, they have all kinds of, they're different in many, many different ways. But according to Einstein's theory, every black hole is exactly the same. There's no features, and the greatest phrase master of all time, John Wheeler, summarized this by saying black holes have no hair. They have no distinguishing features. They're bald objects. Now, just when the classical theory of black holes, just after the 50-year quest to understand Schwarzschild's solution came to an end, Stephen Hawking said, what about quantum mechanics? We live in a quantum mechanical world. how does that, how do we incorporate that? And in fact, because of the uncertainty principle, the edge of the black hole can fluctuate, and something which was inside can suddenly become outside and escape. And there's a very precise formula for this, which Hawking derived. And he showed that black holes radiate like a black body object, like a stove. They radiate in a very characteristic manner of hot objects. And there's a very precise formula for the temperature of a black hole. Importantly, it's proportional to Planck's constant, so it's a quantum effect. Newton's constant is there, and it goes like 1 over the mass. Now, so what Hawking derived was what's called a thermodynamic formula. And I'm writing here, so 2 really great equations. If you have a really, really great equation, and I think there's only 4 in the world, you have it engraved on your headstone. And this development involves 2 of them. So this is Hawking's formula in Westminster Abbey for the temperature of a black hole. It's on the floor between Darwin and Newton. It's the temperature of the black hole is a function of mass. Now, when you give a formula for the temperature of an object as a function, how the temperature changes is a function of energy. That's like if you have a pot of water, you put it on the stove, you add energy from the gas underneath the stove, it heats up. How fast does the temperature rise? That's a formula in the subject of thermodynamics. And there's a different formula for every material on Earth. And in a very beautiful development in the 19th century, Boltzmann showed that all these formulas of thermodynamics can be explained by the assumption that everything is composed of atoms. And then you apply statistical reasoning to the atoms, and from that, you can reduce the laws of thermodynamics to statistics, probability, and what we would now call information theory. And so that was a really good observation, and that went on Boltzmann's headstone outside of Vienna. Now, when you put these 2 things together, you find a formula for the information content. So putting together Hawking's observation, Einstein's theory, Schwarzschild solutions of Einstein theory, Hawking's derivation of a formula, Boltzmann's statistical interpretation of physical laws of thermodynamics, you get out a formula for the number of kilobytes in a black hole. So that has the same meaning as the number of gigabytes in your cell phone or in your hard drive. So what we got from Hawking's work was a number for how much information you can store in a black hole. And it's a very interesting formula. It involves Boltzmann's constant. Interestingly, it involves, and surprisingly, it involves, and we'll come back to this, it's proportional to the area of the outside of the black hole. Now, the number of gigabytes you can put in your smartphone is proportional to the volume. It's the number of chips you can put in. It's not proportional to the area. So this is very surprising that something would have a surprise that we still have not come to the end of, that we don't fully understand. And it also involves Planck's constant, so it's a quantum formula, and Newton's constant sort of involves gravity. We have never encountered a formula like this before in the history of physics. It's a formula which takes a piece from every main area of modern physics and relates them. You know, we have the Einstein equation, which is good for the gravitational force. We have the Maxwell equation, which is good for the electromagnetic force. We have Schrödinger equation, which is good for the quantum system. One equation for every part of physics. This is kind of a master equation that unites all of physics. And it's very exciting for physicists because we don't really understand why there should be such an equation and what its ultimate origin is. Now, one thing to say about it is it's a very big, it's a lot of kilobytes. So all the data in the Google data banks would fit inside a tiny black hole, a trillionth of a millimeter across, far smaller than electrons. And in fact, various Gedanken experiments, a Gedanken experiment is one you do in your head, indicate that there would be a deep inconsistency if anything could have more information than within a given area than a black hole. And this is trouble for Moore's law. So Moore's law says that every 3 years, the number of gigabytes you can put in a given area doubles. And if you take that out for 3 centuries, you'll find that you would need to have more storage than can be achieved by a black hole. Now, since this a conference on AI, I should also mention that black holes are the smartest objects in the universe. We believe they don't just store information, but they can process information, and they can process it. We believe it's a fundamental law of nature that nothing can ever process information faster than a black hole. So you put something in, you throw something in, it spits it out in the form of Hawking radiation. So we can also say they're the smartest objects in the universe. We just can't understand what they're saying because we're not smart enough. But I guess in 300 years, safe to say no one in this room will prove this prediction wrong, but in 300 years, I'm going to predict that we all have a little black hole chip in our brain that will use ChatGPT 10,000, and then we'll be done. That'll be as far as we can go. All right, now if you were listening carefully, you may have realized that I told you 2 things that are completely contradictory. Now, physicists love contradictions because it keeps them in business. And the 2 things were that black holes are the simplest objects in the universe, and the other is that they're the most complex objects in the universe. How is this possible? Well, and this isn't the only problem. The other problem is when they disappear, they evaporate and they disappear, the information inside them is gone from the universe. So the universe is, according to what seems the naive implications of Hawking's theory, the universe is kind of leaky and information can just dissipate out of it. And if that were true, which almost nobody believes anymore, but we don't really understand why not. If that were true, that would be the ultimate nightmare for physicists because it means there are no laws of physics. We can't predict things. There's a kind of inherent randomness in the universe, and the millennial-long project to find all the laws of nature is sort of ended sort of, it's just kind of random. So we don't like that. but we don't think how that works anymore. We don't anymore think that's what's happened. So now I'm not going to say very much. I'm just going to have this one slide on string theory, though I've spent a lot of my career working on it. String theory is a theory. This problem comes about with black holes when you have quantum mechanics and gravity. And string theory may or may not have something to do with physical reality, but we're pretty confident that on a piece of paper, it is a theory which consistently incorporates both quantum mechanics and general relativity, and therefore should have some resolution of this puzzle. And wonderfully it does. So now there's no consistency. I think everybody is familiar with the fact that different people can describe the same situation from different points of view, and they look different, and then maybe you correct them, and finally you come to an agreement in the same place. So there's no really fundamental inconsistency in having two approximate descriptions of the same thing, which sound rather different. And in fact, that's what happens. We found in string theory, of course, string theory contains the Einstein description, it contains black holes, but using techniques available as to string theory, we found that there's a kind of, that the black hole resembles a hologram, that there's a holographic plate that sits on the boundary of the black hole, and that explains why the information content, you can think of all the information content is being stored on the plate surrounding the black hole, and the interior of the black hole is like the holographic image that you see projected from the plate. Now, I'm describing this all in very simple words, but in fact, not only did this require a lot of mathematics, new fields of mathematics had to be developed and solved. This project took 25 years, and in order to see this consistency. But there is a proof in string theory that it is totally correct to say that from one starting point, a black hole is the simplest thing, from the other thing is the most complex. Now, string theory kind of, but that's not good enough for me, because there are lots of black holes up there in the sky, for sure. We're very confident of that now. But we don't know exactly how string theory fits in the world, and we want to understand how the real world black holes work. And now, string theory, at first the calculation seemed very complicated, but later on it turned out, and I'll say a few words about the symmetry later, it really depended on a symmetry, symmetries play a very important role in string theory. And there's a symmetry which emerges out of the space-time near the horizon of a black hole. And since it's only the symmetry that matters, we might hope to see indications of that symmetry in the real world. So here is, so this is what conformal symmetry is. So this room doesn't have conformal symmetry, but objects can have, it looks different. If you take your magnifying glass and look, you keep seeing different things at every length scale. But conformal symmetry, objects with conformal symmetry objects with conformal symmetry look the same on every length scale. And some black holes weirdly have that property. The space-time near the horizon of the black hole, as you get closer and closer, it's self-similar. It keeps, the black hole is actually down a long throat. It takes an infinite amount of time to get there. And space has exactly this symmetry. Not approximately, it exactly has this conformal symmetry. That's an exact statement. Now, that's true of the black holes in string theory, and it was that symmetry that we used to show the consistency between the equivalence of maximal simplicity and maximal complexity. Now, there are black holes in the sky that have this symmetry, and they are the ones that are spinning very fast. Black holes can spin around. We've seen it now, we've measured it, but there's a speed limit. Even the horizon of a black hole can't exceed the speed of light. And the ones that are spinning as fast as they can, when they spin that fast, the region right next to the black hole has that weird scaling symmetry that I just showed. And we can use that to understand for these special black holes, which I'm going to say is a small fraction of the ones that we see in the sky. One out of 30 have this property. And so we feel we understand something about those. There's many things we want to understand about black holes that we don't have, that we haven't understood yet. Now, so physicists get very excited whenever they understand, whenever there's a possibility of a new symmetry of nature. You know, we just spent, I think, $60 billion, the accelerator up in Geneva, to see a symmetry of nature. Symmetries of nature there aren't very many. They're very precious. The symmetry near the black hole and they are the focal point from which we build our understanding. Without any symmetry, we really can't understand much. When we have a symmetry, we can understand a lot more. And recently, just only in the last 3 years, there's been a new type. Okay. Yeah. Does that light, can you see that? Okay, it's a little dim. Anyway, there was a fantastic, 4 years ago now, there's this fantastic picture. I'm sure you've all seen it. And where they took a picture of a black hole in the sky. Though what you see here is the black hole is in there, and what you see in this picture is a ring of matter, of hot glowing matter that's swirling around the black hole, but we know there's a black hole because of this hole. This was an incredible experiment. It was like, the precision that they needed, the size of the telescope that they needed. It was like seeing an orange in New York for me. That's what they did. Very impressive feat. Now it turns out that this black hole, which is known as M87 star, it doesn't have exactly the kind of conformal symmetry that I talked about, but there is another kind. So we started talking. Those people who took that picture were just across campus from me, and we started talking about this and realizing that there's a possibility that this conformal symmetry might be observed, and we predicted it in this paper here, and also explained how you would see it. Okay. Is this light shining on the screen? Can you see that image? No? Is it? It's just a little, that's much better. Okay. Okay, so here's light. That's a black hole in the middle. And you see that the light gets focused, it gets bent and focused. And here we have light that's going around once and twice. And so it can go around multiple times. And so you get a sequence at the telescope. You'll see a sequence of rings. I'm going to play that once more. Whoa, that's not what I wanted to do. Yeah. So there's light that passes by, gets bent a little bit. Now we have, it goes around once. Those form a sharper image. And then now we're going to have the ones that wrap around twice. And they form an even sharper image. And in fact, they can wrap around any amount of times. And this bright feature here is known as the photon ring. And that's what we are planning now space missions to see. And we haven't seen that. What has been seen so far is just kind of a blurred out image of all of this. Now, let me explain it with this picture. So here's a black hole. Here we could see a direct image of someone standing outside the black hole. But the light from this person could also weave its way around the black hole and come back, and you would see another upside down image, right? Because the light from the head would come down and go like this, and light from the feet would come and go like this. But it could also go in front of the black hole and weave around and come out and see you. And it could circle around any number of times. And you could, so you see any number of images of yourself, and they will all get more and more stretched out. And if you solve, I mean, to see exactly how this works, you have to solve the Einstein equation. You have to solve the equation for light traveling in the curved space-time around M87. And you find that the images converge on this ring. And that ring is the same photon ring that we were seeing in the last shadow there. And what is so nice about this is that the relationship between this image and that image only depends on the properties of curved space-time around the black hole. So one of the problems that astronomers have run into in getting information out of that image of the black hole is they don't know much about the matter that's swirling around the black hole. So it's a little bit like being in a department store mirror and trying on some clothes. If you look at straight in front of you, you just learn something about how the clothes look on you. But if you look at all the multiple images from the side, then from the relationship between those multiple images, you could reconstruct the mirror. So here we're interested not in the clothes, in the mirror. What we saw in the last picture was the clothes, but we really want to see the mirror, which is the black hole. So a black hole is a mirror. In other words, if you, if we imagine that camera is a black hole, the light from my face could go around, just graze the size of the camera, swing back and come back, or it could go around multiple times, and so you would see any number of images. And I have here a camera that one of my students probably want the lights on, right? Yeah. Sorry, could we get the lights back on? Is that possible? So you can see, let me start back here. You can see if I wait, but you can see I'm waving. Some of the images are right side up, some are upside down. As I walk towards it, there are multiple images, all converging on the photon ring, and that is the thing that we hope to. That is the thing that we hope to actually see in the sky. Now, in order to see, to make the image of M87, this part has already been done. So to see something very small, to see an orange in New York, you need a very big telescope. And they did the calculation about 20 years ago that in order to see M87, you would need a telescope the size of the Earth. But that doesn't mean you need to cover the Earth with telescope mirrors. These are radio telescopes, and you just need to synchronize all the radio telescopes on Earth into one big telescope. Now, and then you have to synchronize all their data. And that meant taking atomic clocks to each telescope, which lose a nanosecond every few centuries. They're incredibly accurate. You had to take the data from you couldn't send the data from these telescopes over the internet. You had to go down there with a suitcase and fill it up with hard drives. And so it was a very difficult problem, and it took them 20 years to do it. But finally they saw that picture that I'm sure you saw. But now we need a bigger one because we want to see this fine ring. And so we have a plan for that, and many of the space agencies are interested in. Looks like it will happen. Launching a satellite. Actually, we're planning to do an eccentric orbit that will give us the most resolution. And so we're hoping to see this new kind of symmetry of nature and learn more about black holes and see where the adventure to understand the laws of nature will take us next. So thank you very much.
So thank you very much, Andrew. It's one of the best conferences I have ever heard. So thank you very much. Maybe we can ask if we have some questions here. Any questions?
Too high.
Yes.
Thank you very much, Professor, for your very inspiring talk. I mean, I have so many questions, but there is one in the end that can you give us a bit of intuition? What do we mean by conformal symmetry? I mean, we all understand what is symmetry from the three-dimensional intuition that we have, but conformal symmetry, is it something beyond? Or?
Well, so conformal symmetry is the most. It's probably the most beyond the symmetries that we are familiar with, like rotational symmetry, or the laws of physics don't change if you rotate them, or translational symmetry, every point in space is the same, and there's a boost symmetry. That was much less obvious. I mean, Galileo discovered that a long time ago, and then Einstein gave a more refined version of it, and Poincaré, of course. Actually, Poincaré really, that was very near here. Yes, within blocks. And but beyond those symmetries that we perceive with our senses, right, I think that conformal symmetry is the most common symmetry. It's a symmetry in which things look the same. So the laws of physics are the same here as here. You know, there's no preferred point. And conformal symmetry means there's no preferred size. And one of the first observations of conformal symmetry was in 1869. If you take carbon and you heat it up just at the liquid, where the liquid carbon turns into gas, it suddenly becomes opaque. And the reason it becomes opaque is right at that point, it acquires a self-similar, the structure of it, the excitations of it have a self-similar structure, which means that every wavelength of light can be absorbed. So, you know, like the air here, okay, it's transparent to some things, but not to other wavelengths. It's the most common. So in condensed matter physics, which is the study of materials, is, I would say, organized around conformal symmetry. That they look for special situations where conformal symmetry appears, and you know, many Nobel Prizes over the last century could, in some form or another, be attributed to a new discovery of conformal symmetry in a new context. What's new is discovering conformal symmetry as a result of curved space-time. And it's new, and it's much weirder. And, you know, Einstein equation does predict that we get space-times that have a similar scaling transformation. And we want to see that.
Can I follow up, perhaps?
Yes.
Yes, thanks a lot. Do you think then, in this case, that there may be other kind of symmetries that we cannot observe because our cognitive capacity is not enough, and perhaps artificial intelligence could, if we give it many high-dimensional data? Of course, this is more visionary, but...
Well, you know, I'm not worried artificial intelligence is going to put me out of work. But, you know, because there's a certain kind of, you know, theoretical physicists spend most of their time, scientists in general, sort of wandering around lost and confused, and every once in a while they stumble into things. Maybe computers could do that too, right? I don't know. But I do think that a lot of this science involves huge data sets. In fact, it's possible that this Event Horizon Telescope, yeah, I think it's true that this Event Horizon Telescope was, by some measure, the biggest data set that was ever produced. They kept up with Moore's Law. In other words, they would not have been able to do it 10 years earlier because there wasn't enough data storage capability in the world. And of course, CERN, which is 2-hour train ride from here, that's also a huge data set. And I think that could well be ways, both in particle physics and astronomy, of getting information out of those data sets that that we haven't thought of yet, and that artificial intelligence could figure out, but hasn't happened yet. Some people are trying to do things like that. Hasn't happened yet.
Thank you.
Question? Another one? Yes, Sandra?
Excuse me, because I'm not a physicist, but you talk about quantum theory. If we have two intricate particles and
Entangled.
Have what? Two?
Entangled.
Entangled. Yeah.
I send one in the hole and one outside.
Yeah.
Will we have information about the hole?
Well, so that is exactly the kind of thing that question that got people really upset.
That is a very big
And Hawking argued famously in 1974, no, information was gone. Okay. And I would say in 1985, half the people in the world who thought about it believed it, the other half didn't. But then after it was shown that's in string, so the answer in string theory is yes, that you don't lose anything. You don't have to give anything up, And the way that worked was so compelling and beautiful, and there's no reason that the real world couldn't use the same mechanism, whether or not string theory describes the real world, that everybody who thinks carefully about this problem, there might be 1,000 people in the world, including Stephen Hawking, except for two people, are persuaded that the information is retained, that you don't lose the information. However, physics is not a democracy. Just because 900, we don't, it's a question of betting, right? So I have to decide whether I'm going to try to make sense of information being destroyed, or I'm going to try to find a way of understanding how information isn't destroyed. I have to make that bet. I don't know. Nobody knows. But we have to bet, and out of 1,000 people, 998 are betting that it's still there, and there's two that are betting that it. And Hawking himself, after the work on string theory, changed his mind.
Okay, thank you. Thank you very much, Andrew.
Was great.
Everybody, thank you again, Andrew. Thank you again.
Thank you.